4. Something I wanted to write down before we start this is in physics, energy is equal to force times displacement. Well, force is a vector, displacement is a vector, but the answer, energy, is a scalar. Energy is a real number. So I wanted to motivate our lesson with a little physics here, that energy is force times displacement, and the product of those two vectors is actually a scalar. And you should remember from the previous lesson that a scalar is just a fancy word in physics for a real number, okay, versus a vector. All right, so we have a definition of the dot product. And again, let me recap as you're writing this information down, is that in the previous lesson, we looked at scalar multiplication. We looked at taking 2 times a vector, or negative 3 times a vector. Well, we still got a vector out when you take a scalar times a vector. We even looked at adding and subtracting vectors. And when we added and subtracted vectors, we got a vector. Well, in physics, when you multiply 2 vectors, they don't say vector multiplication, they call it the dot product. Why? I'm not 100% sure. But they call it the dot product, and it says if you have vector u in component form, u sub 1, comma u sub 2, ask Mr. Corner why they call it that. Vector v is the component form v sub 1, v sub 2. The dot product is actually very easy, but this is put on your index card, okay? You take u sub 1 times v sub 1, so that's the first components, you multiply them, plus u sub 2 times v sub 2, like the second components. Notice the product is a scalar. This is very, very easy. So what you're going to do in example 1, letter A, is you take 4 times 2 plus 5 times 3. That's 8 plus 15. So the dot product is a scalar. All right, you guys try B and C. I'll give you a head start. On your mark, get set, go. I'm going to erase you. All right, letter B, did you get 0? And C, negative 6. So very simple stuff. Now, in example 2, we've got 3 different vectors, u, v, and w. It says find each product. Now, before you start this one, I want to make sure that we're always keeping our thinking caps on. Sometimes we can go on autopilot and we're like, okay, I'm just doing and doing and doing, and we're not thinking anymore. Now, I want you to think a moment. If I do u times v, or do the dot product, what comes out of the dot product?
Scalar.
A scalar. And then I'm going to take a scalar times a vector. What comes out of that?
Vector.
Oh, so when you multiply 3 vectors, we're going to get a vector.
So it's kind of like negatives.
It's like what?
Like if negative times a negative is a positive. But
Yeah.
if you got 3, then it's negative.
Yeah.
Sure.
I had to think a moment. So, is it like a negative? Yeah, I got you. I followed you. All right, so here we go. Let's do vector. Oh, what am I doing there? I don't know. All right, let me try that again. So I'm going to take vector u, which is negative 1, comma 3, and do a dot product with v. I'm going to take that result, which is going to be a scalar, now, if you're getting the hang of it, I can do the dot product in my head, but I was trying to show you like how you do it. So this is negative 2 plus negative 12, that's negative 14. So once you get the hang of it, you don't have to show the work for a dot product. And then you're going to multiply the scalar, so you get negative 14, comma 28. Very simple, okay? Very simple. Now letter B says we want to take vector u times 2 times vector v. So here's vector u, negative 1 comma 3, and I'm going to multiply. Let's go ahead and do 2 times v. That would be 4 times negative 8. Then you'll do your dot product. So that's what? Negative 4 plus negative 24. So I got negative 28. All right, any questions on that? Very, very simple stuff. Everybody okay? All right, now, I love example 3 because this is taking us up there, very analytical, very abstract mathematics. I like that. Example 3 says the dot product of vector u with itself is 5. What is the magnitude of u? Well, when you first read that, you're probably like, huh? What are you talking about? And so let's start piecing this together. If vector u is a vector, we can say, all right, vector u has components u sub 1 comma u sub 2. The dot product of u with itself is 5. So that means if I take u sub 1 comma u sub 2 and I do the dot product with itself, it's saying the dot product is 5. Well, that's u sub 1 times u sub 1 plus u sub 2 times u sub 2. And so I'm really, whoops, that's supposed to be an equals. So I'm just playing the game, what do I know? What do I know? And you just want to keep asking yourself questions. So then it's asking me, well, what's the magnitude of u? All right, well, I want to ask myself, what do I know about that? If its component form is u sub 1 comma u sub 2, I know the magnitude would be the square root of u sub 1 squared plus u sub 2 squared. Is anybody seeing a connection now? What do we know?
It's the square root.
Yeah, you know u sub 1 squared plus u sub 2 squared is 5, so the magnitude is the square root of 5. Crowd goes wild. Exciting! That's so exciting, isn't it?
I would just square whatever number it is.
Yeah.
But can you see how I started with what do I know? If I'm doing a dot product, what do I know? Multiply it, multiply it. Okay, then what do I know about a magnitude? And then there was a connection between the two.
What a beautiful problem.
That is, thank you, Adam, thank you. I like that. All right.
That was sarcastic.
No, in my world, he's sincere, okay? The next definition, and definitely I would include this on my index card, the angle between two vectors. If theta is the angle between two non-zero vectors, we'll call it vector u and vector v, then there's a formula we have, cosine theta equals the dot product over the product of their magnitudes. And I'm trying to remember, the other class asked me about a homework problem.
I think it was like this.
Yeah, and I'd like to do that one with you because it's a really fantastic problem. You didn't know this formula, so you were not expected to use this, but you actually could find the distance of each side. You could do the magnitudes, and then you knew those 2 points. You can find the distance between those 2 points, and you did law of cosines.
That's what I tried to do.
That's
You
what
got
I
it
told
wrong?
you.
Okay.
I tried.
Well,
Use the
after we
opposite
finish
side.
this, we'll do that problem because that was an excellent problem. Okay, example 4 says find the angle between vector u and vector v. Well, of course we're just going to go through the crunching of this, but what I'd like us to do first is let's draw a picture. Okay, let's draw a coordinate grid, and we are going to graph these two vectors. I have 4 comma 3, so that's vector u, And then I have 3 comma 5. Remember, that's component form. And so what I'm talking about is I'm trying to find the angle in between the two vectors. That's actually what I'm trying to accomplish. So the cosine of theta, according to this formula, is the dot product divided by the product of their magnitudes. So off to the side, you want to go figure out their magnitudes. The magnitude of vector u would be the square root of 4 squared plus 3 squared. Well, that's a 3, 4, 5 right triangle. Vector v is not. It's the square root of 3 squared plus 5 squared. 25 plus 9, that's 34. Now you can tell this is an acute angle, right? It's definitely smaller than 90 degrees. So if you're really thinking here, this is going to be 12 plus 15, isn't that 27? This is some positive number. So when I do inverse cosine, if you remember from chapter 4, inverse cosine spits out values between 0 and 180. It's positive, so it's 0 to 90. Okay, now you have to be very, very careful. In my other class, when we did this, we actually got the wrong answer first, because even I entered it wrong. But it was a good thing. So let's go ahead and go through how you enter this. And I want to show you that, in fact, it does matter how you enter it. Don't do it the way I do it first, because I want to show you how to do it wrong so you don't do that. Press mode, check your mode, check your mode. The angle in between, it would make more sense to describe it in degrees. So check your mode, make sure you're in degree mode. So I'm going to do second cosine. And if I take 27 divided by, whoops, what was that? 5 radical 34, it's actually going to give me an error. And it should give me an error. It says domain. Do you know what I actually told the calculator to do, even though it's not what I meant? I told the calculator to take 27 divided by 5, figure that out, and then multiply by square root 34. So that's definitely bigger than 1, and that's out of my domain. So watch how you are actually supposed to enter it. So now do it with me. If you have a product in the denominator, you need to put that in a parenthesis. Close, close. Notice you're going to have 2 parentheses on the right. And so you're getting about 22.2 degrees. So notice very carefully how you're supposed to enter the denominator. So that angle between is 22.2 degrees. And that makes sense, just eyeballing it. It's a pretty small angle. There is an alternate form of the dot product. We don't see it that often, but depending on, if you're going to do physics next year, this might help. All we've done to get this alternate form is we've multiplied both sides by the product of the magnitudes. That's the only thing, okay? All right, then we have another definition. Definition of orthogonal vectors. The vectors u and v are orthogonal if the dot product is 0. In physics, orthogonal is the word they use for perpendicular. To describe vectors are perpendicular. So don't you remember when we were just learning about the dot product? One of them had a dot product of 0, didn't it? Do you remember that? I want to go back there a moment, and I want to look at the 2 vectors. And I'll come back to this if you need to. But let's go back to example 1, letter B. And I want to plot these 2 vectors. 2, -1 is this vector. 1, 2 is this vector. Look at that. Isn't that cool? They are perpendicular. They're orthogonal. So if you know 2 vectors, now let's make a neat connection here. If the 2 vectors are orthogonal, what's the angle between them? 90 degrees. Ah, okay. That is pretty cool. Cool business. All right, anybody else need that? Orthogonal means perpendicular. This is not bad. Now you can see why it's a one-day lesson, right? Zip, zip, zip. Are you okay? All right, example 5 says, are the vectors u and v orthogonal? So what do you have to do? Multiply them. Do the dot product. So take 2, -3 times 6, 4. So that's what? 12 plus -12, which is 0. So it's yes. All right, many applications in physics and engineering require a vector to be broken apart into the sum of 2 vector components. So my son has been doing a lot of work like this in his college physics course, so he's been showing me different things that it's like really jumping out at me as, wow, that's really, really important. In order to break them apart, we use this formula for a projection of u onto v, and that's the way that you break it apart. So here's the formula. And again, what this formula is doing is it allows you to break it apart. You take the dot product divided by the magnitude of v squared times the vector v. The only thing I'm going to ask you to do on the next quiz is to find the projection of u onto v. It's very, all you're going to do, so you're going to write that formula down on your index card. And so if I want to do the projection of u onto v, we're going to take the dot product, 3, -5 times 6, 2. Let's do the magnitude of v. That's 6 squared plus 2 squared. I don't want to bother simplifying the radical because I'm just squaring it, right? Squaring the square root 40 is easy. But if I simplified that to 2 radical 10 and then I square it, yuck, that makes it difficult. So that's over 40 times the vector v. And keep in mind, some of this you'll need to wait till physics to see why you wanted to do this. I'm just showing you the math of it. So this is what, 18 minus 10, right? Yeah, 18 minus 10 is 8 over 40. So that's 1/5 times the 6, 2. So it's 6/5, 2/5. So again, very, very straightforward.